Welcome to this tutorial on integer programming for visual computing. My name is Peter Wonka and I will present this tutorial together with my colleague Jihan Peng. For our notation, we will try to denote matrices with uppercase boldface letters and vectors with lowercase boldface letters. Scalars will just be written normally without using boldface. We start out by introducing an optimization problem in general form. Just a slight side note that different authors propose slightly different versions of what the general form is, so the general form is not something that's universally accepted. We'll just use this particular form. We would like to minimize a function f of x, where x are the variables of this function f, and we would like to minimize this function, and that means we would like to find an assignment to the variables. We would like to find values for these variables. There are a set of constraint functions gi. These constraint functions gi also take the variables x as input, and in this general form our constraints all have the form gi of x are smaller equal to some scalar bi. And as we see here, we have m such constraint functions. The function that we try to optimize, f of x, is also called the objective function. The variables x are split into two groups. The first group are integer variables, so these have to be an element of z, and we have n1 such integer variables, and the second group of variables can be real numbers. So the total number of variables is n, which consists of n1 plus n2. The feasible region then has to combine the restrictions of the constraint functions and the restrictions of this the fact that several variables have to be integer variables, and so the feasible region f is defined as the set of all points x that are element of z to the power of n1 times r to the power of n2, for which the constraint functions hold. A solution is an assignment of values to variables. And often we are interested in an optimal solution x star that has the smallest value of f among all feasible solutions. There are two competing terms that are being used. One is optimization and the other one is programming. I believe that programming is mainly used for historical reasons, because many years back people started to introduce optimization ideas under the term programming. If I could decide, there would only be the term optimization. However, if you go to look for books about optimization using integer variables, you will find a lot of books that are called integer programming, and also when you search on the web you'll find a lot under the term integer programming. So we will use both of these terms interchangeably in this course. First, let's introduce linear programming. linear programming is a specialized form of the general optimization that we just introduced before. In linear programming, the objective function is limited to the form x transpose C, where x are the variables that we try to optimize for, and C is a vector of constants. So we have n variables x, and therefore this vector C also needs to have n components. By computing C transpose x, we obtain a dot product between two vectors, and every variable in x will have one coefficient. The m constraints are also all linear, and they can be written in the form ax smaller equal to b. A is a matrix that is an element of R m cross n, so we have n variables and m equations. Each of the m rows of the matrix defines the coefficients of one linear inequality. While superficially that just looks like one equation, in reality these are m separate equations. B, element R to the power of m, is a vector, and each entry bi is on the right hand side of the ith inequality. Also note that this smaller equal sign is overloaded. So what we have on the left side is a vector, and on the right side is another vector, and then for each dimension component of the vector on the left, we want to make sure that this component is smaller equal to the component. Here are examples of linear programming. This is an example of two variables and two constraints. We're trying to find values for two variables, x1 and x2, and the objective function is c1 times x1 plus c2 times x2. c1 and c2 are constants. And then these are two inequalities, and a11, a12 are the coefficients constants for the first equation, and a21 and a22 are the coefficients for the second equation. And then if we look at how we presented this in the slide before, then all these a coefficients would be collected into a matrix. On the right hand side we see the elements of the vector b, so b would have two dimensions here, so we have b1 and b2. Then an even more specific example we see at the bottom, where we use arbitrary numbers to make it clear what are the constants and what are the variables. So for example, we would like to optimize minus 4x1 minus 2x2. So in our form we want to minimize this objective function, and then we have two constraints. If you look at the second constraint here, this is just an example to visualize that not every variable needs to be involved in every constraint. So here, for example, the coefficient for x2 would be 0, and the variable x2 is not involved in the second constraint. Here is a graphical example. We are first going to look at the inequalities. Here I took the liberty to flip the sign around. So we look at this inequality x1 greater or equals to 0 because just it's more intuitive to interpret. So let's look at the inequalities x1 greater or equal to 0 and x2 greater or equal to 0. So x1 being greater or equal to 0 means that we are only considering variable assignments that are, like if you look at this space, and every point in this space is one possible variable assignment to x1 and x2. So x1 greater or equal to 0 means that we're only considering points in this space here. So this equation gives a half space, so all the points that are anywhere here are considered. Then x2 greater or equal to 0 means that only points up here are eligible, so we kind of restrict the solution to any point up here. And then the intersection between these two half spaces gives the quadrant on the top right. To graphically determine the solution, it makes sense to draw the linear equation for each of these inequalities. So we're going to draw x1 equals to 0 and x2 equals to 0. x1 equals to 0 is going to give this line going up here. I'm just going to draw it that long. And then we have x2 equals to 0 is going to give a line. Again, I just draw a section of the line. It's going to go over here. And what we will end up with in the end is the intersection of four half spaces. And these two red lines that we drew now are two of these boundaries of the valid region that is shown here in yellow. Now we need to look at the first two inequality constraints for constructing this line and this line. So one of these two lines is 50x1 plus 31x2 smaller equal to 250, and the other one is 3x1 minus 2x2 greater or equal to minus 4. What we can observe here is that the yellow region, that is the feasible region, is a polygon, and that it is a convex polygon. Next, we would like to explain this orange line here, that is a visualization of the objective function. So we go back to the equation. The objective function is 100x1 plus 64x2. And in the graphical representation, we're just taking this objective function and we draw it anywhere in the figure. So the main thing is the slope, but we actually don't know how far to shift it. So we can take this line representing the objective function and shift it either to the right or shift it to the left. The fact is that no matter where we shift it, all points on this line will give the same function value. So for example, if we shift this line so that it goes through the origin, so the slope has to be the same, then all the points on this line will be assigned the function value 0. Since in our example we are actually having a maximization problem, we would like to find the point that is an intersection of this line and the feasible region in yellow. that is the furthest to the right. So we want to find the point that just touches the feasible region, but that is as far shifted to the right as possible. And this is going to be this point here, which is the optimum at some ugly value that is written here. How can we solve a linear programming problem? So first, there's no analytic formula for the solution. However, reliable and efficient algorithms and software exist. Example algorithms are the simplex algorithm and interior point algorithms. The computation time is proportional to n squared m. N again is the number of variables, m the number of equations, if m greater or equal to n, and computation time is less if there is a specific structure in the problem. Formulating a problem as linear programming problem is already non-trivial and requires some practice. Next, we're making the step from linear programming to linear integer programming. Looking at the formulation, at a first glance, it seems that nothing has changed. The objective function is still linear, C transpose x, x are the variables, and the constraint functions are ax smaller equal to b. So the difference between linear programming and linear integer programming is merely in the definition of the variables. So if you have floating point variables, that means x is an element of Rn, then we have linear programming. If x are integer variables, so x is an element of set n, then we have a linear integer program, or IP for short. An important special case of integer programming is integer programming with binary variables. For binary variables, we have x is an element of 0, 1 to the power of n. That means x is a vector that has n components, but each component is restricted to be either 0 or 1. A fourth option is that we have a mix of floating point and integer variables. This will be called mixed integer programming, or MIP for short. That means that x is split into two groups of variables, x integer and x float, where we have xf is an element of Rn1 and xi is an element of Zn2. So the n variables are split into two parts. The first n1 variables are floating point and the second n2 are integer. I mean, the order doesn't really matter. That's just some arbitrary convention. There are variations of this standard form. While we do write this standard form as minimization and maybe with smaller to equal, these things are somewhat arbitrary and many other variations exist. So you notice that even in my own graphical linear programming example, I violated this standard form. So for example, switching minimum and maximum is a fairly trivial change. If you would like to maximize some function, you can minimize the negative of the function. Similar simple sign flips allow you to switch smaller equal and greater and equal. So therefore it's also easy to bring any inequality in standard form. Now, a bit more difficult, we're not going to go into exactly how to do it. It's still very simple, is the idea to use constraints that have an equality sign. So there could be something else, maybe something like, let's say, bx, would be nice to be able to draw a bit nicer, where b is another matrix equals to something else, let's call it d. And x and is a vector of variables, and d is another vector of, that's on the right-hand side, is another vector of constants. Another variation is that some of these standards forms actually require that all variables have to be positive. So for each component of x, there's an implicit constraint that x1 has to be greater than 0, greater equals 0, x2 has to be greater equals 0, and so on. So here's another optimization problem that, while it's not in our standard form, could be easily transferred into the standard form. So some comments about formulations. First, let's define the term polyhedron. A polyhedron P is a subset of Rn that can be described by a finite set of linear constraints. So a polyhedron P are points x in Rn that are described by a set of linear inequalities. For example, ax smaller equal to b. The next definition requires a bit of thinking. A polyhedron P that is a subset of Rn1 plus n2 is a formulation for a set X that is subset of Zn1 times Rn2 if and only if X equals P intersected with Zn1 times Rn2. In integer programming or mixed integer programming, we are concerned about values that live in this space or set where the first n1 variables are integers, so this is this set n1, and the second n2 variables are floating point values. But this set is more restrictive than r to the power of n1 plus n2, where all the numbers are real numbers. So in this x, the first n1 dimensions are integers, and here the first n1 dimensions can be real. So therefore also this polyhedron P has more numbers in it, more points in it, than this set X. And we would like to have a polyhedron P that has some more numbers in it than the set X, but not too many numbers in it. So specifically, if we have X, the set, and we add a lot more real numbers to the set, that is allowed, but we are not allowed to add any more integer values. So when we intersect the polyhedron with this space set at 1 times r and 2, then we cannot have any additional integer values. Now, a convex combination of points from a set S, x1, x2, xk, element of S, is a point of the form theta 1 x1 plus theta 2 x2 plus theta k xk, where all the thetas are greater or equal to 0, and we have a sum from I equals to 1 to k, summing up all the theta i's gives exactly 1. So we're taking a weighted combination where the weights sum to exactly 1, and all the weights are greater or equal to 0. A set S is convex if and only if any convex combination of points in S is in S. So I kind of wrote this for arbitrary sets. So generally this is some maybe Rn, and then these x1 to xk would be vectors. Finally, the convex hull, also written as conv S, is the set of all convex combinations of points in S. So, as described before, if we have a formulation has to enclose all feasible integer points, but no infeasible integer points. So there's some wiggle room in as to how many of the real points that are not integers it can contain, but it's not allowed to have any infeasible integer points inside of it. Now, when we talk about the runtime, then the runtime depends on factors such as the number of variables, that's pretty obvious, the number of constraints, that is also pretty obvious, but there are some things when it gets a bit more tricky. For example, the tightness of fit. So just to repeat the obvious connection to mixed integer programming and integer programming, if we are specifying the constraint functions, the constraint functions are specified in the form ax smaller equal to b. And if we are exclusively in real space, this would give a polyhedron P. And this polyhedron P describes a formulation for a set X. These are all the feasible solutions if we now think about the first n1 variables being integer. And then this polyhedron has to be tight enough so that it only includes feasible points, but there's this wiggle room how many other real points are in there, and how tighter the fit is of this polyhedron, the better. So if we think about a set of feasible points, again this X set n1 times Rn2, there will be many different possible formulations, and we would like to find a formulation that is as good as possible, and generally speaking, a very tight formulation is better than one that is not tight. So a formulation A is at least as strong as B if A is a subset of B, but not necessarily a proper subset. A formulation A is stronger than B if A is a proper subset of B. That means there are points in B that are not inside of A. And so A is really a smaller set. A formulation A is ideal if the convex hull of all the feasible solutions equals to A. Let's practice with a graphical example to see that we properly understood these definitions. What we look at here are 4 constraint functions, and they will define a convex polygon. this is now a pure integer program, so we have two variables, x1 and x2, that should be integer. We're not gonna look at the objective function right now. What we see here is a figure that looks almost identical to the example that we used for linear programming. For the linear program, the feasible region was shown here in yellow. However, for this integer program, this region in yellow is what we call the formulation. And the formulation contains, is this polyhedron. It's convex again, and in 2D it's a polygon. Then it contains integer solutions that are feasible, and it contains a lot of real numbers that are not integer. And all the integer values inside this feasible region are visualized by these blue circles. So for example, this is a blue circle here, this is another one here, and we visualize the coordinate system by these dashed lines in x and y direction, and then at the intersection of these dashed lines, this is where the integer coordinates lie. For example, this is one integer coordinate, but it's outside of the formulation, so it's outside, or it's not a feasible point. And note also that at the boundary, there are some points that are here, because the equations are x1 greater or equal to 0, x2 greater or equal to 0. So there can be integer points on the boundary. So for this formulation, what we require is that when we change it, it would still be valid. We don't add any extra points. So, and to make the formulation better, we would like to make the formulation a tighter fit. So for example, we could add another constraint that cuts off this part here. So we could add a constraint here that eliminates this part here. And that would also be a valid formulation, and in fact it would be better because it's a tighter fit. But we could also try to make it worse. So maybe we add some extra points here. We just got to be careful not to hit any integer points. So we could go maybe up here, here, and go back here, then maybe go up here. So then again, we are convex, but we could kind of enlarge the polygon a bit without adding any integer points, and it would also be a valid formulation for this feasible set. Now looking at this objective function again and trying to find the maximum value, so the point in the feasible set. Now the real feasible set, only the blue points, where this function obtains the maximum, we will see that the integer optimum is actually down here. And to go back to a few slides, then we remember that the floating point optimum, or the real number optimum, was up here. This is a simple visualization of the fact that the integer optimum can be very far from the floating point optimum. Another thing that we want to visualize here is that rounding is not a feasible approach. For example, this is the floating point optimum, and so we could just say, okay, let's snap to the closest integer point, which would be this point here, but this is not a feasible solution. But still, people might object and say, okay, well, how hard can it be? Just unlucky, so maybe I'm here. So what I would like to do is I'm gonna try this point and this point, and also then maybe I'm going to try this point, and I'm going to try this point, and then obviously there's going to be some integer solution close by. So basically, there's no need to use this integer programming. I can just go in and try a little rounding, and then I will have a solution. In addition, while maybe the optimum can be quite far from the real integer optimum, this rounded solution, this must be quite good. I mean, it can't be that the objective value is that much different. So by just doing a little rounding, I will get the solution that's already pretty good. I just get an approximation, and I don't need more anyways. So this intuition is unfortunately completely wrong. And in many cases, it will be quite difficult to actually find a single feasible solution. So the reason to use proper technology for solving integer programs is not because we are afraid of a little approximation error, but it's really that the problem is inherently difficult enough that it requires more sophisticated techniques. Let's discuss 3 different components of the optimization. The first component is modeling. We have an application problem. How can we formulate this application problem as a standard optimization problem? This will be the main purpose of the following slides. Then we have algorithm development. How can we derive new optimization algorithms for standard optimization problems? Or how can we derive new optimization algorithms for specialized optimization problems? The first part, finding new solutions for standard problems, is of course a lot harder, and it can benefit a lot of people, so therefore it is also quite important. However, that's typically not done in the context of visual computing. New optimization algorithms for specialized optimization problems, such as specialized problems occurring in visual computing, is something that multiple people work on. Now, this is a bit a philosophical debate. I'm just presenting my own opinion. So many times I would argue that while people derive new optimization algorithms, they might not have actually necessarily benefited a lot from it. It would have been better if they actually would have learned to use standard tools properly. It's actually not that easy to develop new optimization algorithms. And therefore, also I put more emphasis on modeling, because I believe, especially when you start out, it is much more beneficial to properly use modeling to model a problem correctly and then use a standard solver. And the difference in modeling, so modeling the same problem in different ways, can still be significant, where one way to model it can be orders of magnitude slower than another way to model it. Finally, I would identify theory, where we're talking about finding convergence guarantees, bounds, and so on of optimization algorithms. Again, so if we look at this specifically for visual computing, then we can observe that people work on modeling, they work on algorithm development, they also work on modeling plus algorithm development together, but rarely do people work on theory in visual computing. Now, to solve an IP problem, you can use a standard solver that's available in MATLAB, Gurobi, or MOSAC, and see what happens. There are academic licenses for, I think, Gurobi at least. I don't know about MOSEC and MATLAB. I guess MATLAB no. And one other thing to consider is that the quality of these solvers can be very different. So my recommendation is to use Gurobi. And the difference can really be orders of magnitude, or it can be the difference between working well and crashing or not converging to anything after days. Alternatively, you can create a new heuristic solver. Also consider that a heuristic solver can be a heuristic that is built on top of one of the standard solvers. For example, a heuristic that is built on Gurobi, to give some intuition how an integer program or mixed integer program could be solved. We'll discuss the branch and bound algorithm on a high level. Actually, this is specific enough that you could almost go and implement it. It's just that there might be thousands of lines of code of optimizations for making certain details much better that are not discussed here in this very basic outline. All right, since we talked about branch and bound, let's first think about bounds. How can we create an upper and a lower bound for the objective value of the solution? We assume that we try to minimize the objective function here. So if we run the linear program that does not have any of the integer constraints, we call that the LP relaxation. And if we use this LP relaxation, that gives us a lower bound for the optimal solution. So the optimal solution cannot be better than this. Further, any particular feasible solution is an upper bound for the optimal solution. So in case where we can find at least one feasible solution, we already have gained something that is an upper bound. And in the case that one feasible solution that is fairly close to the lower bound, then we can know already that we have a pretty good approximation available. So let's say we start with our problem, and then we run an LP relaxed version of the problem. And then we look at the solution, and we can distinguish three cases. First, the linear program comes back and tells us it's infeasible. If the linear program is infeasible, we know that the mixed integer program is also infeasible. If the optimal LP solution is feasible, but it's also feasible for the ML, the mixed integer linear program, then we know we have found an optimal solution. For example, if you have a pure integer program where all variables are integer, and we run the LP, the relaxation, and all variables turn out to be integer, we know we have found an optimal solution. Otherwise, the linear program is feasible, but it's not it's not a feasible solution for the integer program, then we know we have a lower bound. So the first two cases tell us basically that we're finished. Either bad luck, no solution, or we have found an optimal solution. When we start out, or most of the time, we would expect that the third case is the dominant case. That is, we found a lower bound, but it's not the optimal solution to the integer program. And this case is something that we would like to break down into two simpler problems. So how can we now branch on this third case recursively? The most common way to branch is to do the following. We select a variable I whose value xi is fractional in the LP solution, and then we create two subproblems. We look at the value xi hat, that is a real number, and then we round it down. And in the first subproblem, we add the constraint xi smaller equal to what is rounded down. And then the second time we kind of round it up, and we add a constraint xi smaller equal to this rounded up value. So for example, we start with the complete problem, and then for one reason or another, we select a variable that has an assignment that's not integer. So in this case, we select x3, it's 5.7, and then we branch on this variable, and we add one constraint x3 smaller equal to 5, and then we create a new problem that we try to solve here, and then we add x3 greater equal to 6, and then we create a new problem that we try to solve here. And then this proceeds recursively. Maybe here we have some variable x 117 that is in the LP solution is equal to 6.7, and then again we branch with x 117 smaller equal to 6 and x 117 greater or equal to 7. This concludes the introduction to integer programming, and next we will look at example problems that are of relevance to visual computing.